Welcome to your personalized deep dive. Systems theory and complexity science. Looks like you've done some reading on this.
Quite a bit, yeah. It's a really interesting area. Moving past that simple cause and effect view of the world, seeing how everything's connected.
Right, so no more like breaking things down to the smallest pieces. Now we're thinking about relationships and how things interact.
Exactly. It's kind of like how understanding nature's laws talks about it. All those natural laws about how things grow and spread and balance. It's not just a bunch of separate principles. They all work together, to create all the complexity we see.
I see. So instead of looking at a tree and just seeing its parts, the roots, trunk, leaves, we're thinking about how it interacts with everything around it, the sunlight, the soil, even the bugs living on it.
Yeah. And you know what's really neat? When you start thinking this way, you can start to grasp these really complex problems, like climate change or how the financial markets work. Heck, even our own bodies are a great example.
Makes you think differently, huh?
Yeah.
It's like appreciating the entire forest instead of just getting stuck looking at one tree.
Now, Chapter 10 in our source material dives right into systems theory and complexity science. Seems like the perfect place to start our deep dive. It is, and right off the bat, it tells us to move past that reductionist view, breaking things down to the tiniest bits. Instead, we need to understand how all those relationships and interactions work within a system.
Okay, so rather than taking apart a clock to see how it works, we should be looking at how all the gears and springs interact to tell time.
Exactly. It's all about seeing the bigger picture, how all those tiny interactions add up to create something way bigger than just the parts themselves.
Gotcha. Now, the chapter talks about feedback loops. I got to admit, when I hear that term, my mind goes straight to social media and how those algorithms keep you hooked.
But feedback loops are way more than just social media. They're everywhere in nature, and they're essential to understand how systems work. It's like a constant cycle of cause and effect.
So it's not just A causing B, but then B loops back and influences A again.
Precisely. The output of the system becomes an input, shaping how the system acts. There are two main types, positive and negative.
All right, following you. But what's the difference between those two? Positive and negative feedback.
So positive feedback, it kind of like ramps things up. It pushes the system further away from where it started. Think about a microphone too close to a speaker, that awful screeching sound. That's positive feedback, the sound getting amplified over and over.
Yikes, I can hear it now. So it's kind of like a runaway train, just gaining more and more speed. What about negative feedback? Does it work the opposite way?
Yeah, in a way, negative feedback tries to stabilize things. It keeps the system within a certain range, like a thermostat. It turns on the heat when the room gets too cold, then shuts it off when the room warms up.
Like a balancing act, keeping things steady. Is there an example of negative feedback in nature?
Oh, tons. Think about predators and prey. If there's suddenly a lot more prey animals, the predators have a feast and their population grows too. But then, with more predators around, they eat more prey and the prey population goes down, brings everything back into balance.
That's a classic example. But can these feedback loops cause problems, especially in human systems?
Oh, absolutely. Especially those positive feedback loops. Sometimes they're good, but they can also get out of hand. Think about how misinformation spreads online. One sensational story gets shared and reshared, and it just keeps growing, even if it's not true.
So if we understand how these feedback loops work, we can maybe design systems that are tougher, less likely to just spin out of control, right?
You got it. It's about recognizing those patterns, then building systems that can handle change and stay balanced.
Okay, starting to see how this all connects. We've covered systems thinking and those feedback loops. What's next in our complexity science adventure?
Welcome back. Glad to be diving deeper into this with you.
Same here. We've covered some good stuff already. Now I'm curious to see how these ideas about, everything being connected play out on an even bigger scale.
Well, one of the coolest things about these complex systems is the whole idea of emergent properties. And that's where we're heading next.
Emergent properties, huh? That sounds kind of mysterious. Is that like how unexpected behaviors and patterns arise from simple interactions, like the whole being greater than the sum of its parts?
You got it. Think about a city, right? All those people rushing around doing their own thing. Individually, it might seem random, but collectively, they create this complex, vibrant pattern of urban life.
So it's not just about individual actions, but about how those actions, when they come together, create something totally new and unexpected.
Exactly. And understanding nature's laws really dives into this in Chapter 10. It gives us some awesome examples. Remember that flock of birds we talked about? Each bird's just doing its own thing, but together they create those amazing synchronized movements, like some kind of natural ballet.
It's incredible how those simple interactions can lead to such complex patterns. Are there other examples of this?
Oh, tons. The book also talks about the human brain. Each neuron is just firing signals, but from all those interactions, consciousness emerges. Or even something like a snowflake, just water molecules following basic physics, but they self-assemble into those unique, intricate patterns.
It's like there's this hidden layer of complexity waiting to be revealed when things interact in the right way.
You nailed it. Emergence shows us that just looking at the individual parts doesn't always tell the whole story. It's the way they come together that creates something entirely new and often unpredictable.
So we've seen how all these individual components interact and create these emergent properties, but is there a way to understand how complex systems will organize themselves?
Yeah.
It seems like there must be some kind of guiding principle, right?
That's where self-organization comes in. It's this wild idea that systems can basically arrange themselves into these intricate patterns, all without any central control or outside guidance. It almost seems impossible, but order can actually arise from chaos.
Is that like those sand mandalas? The ones
Ah.
that form from vibrations on a metal plate?
Perfect analogy. Or think about sand dunes forming in the wind. No blueprints, no architects, but they create those beautiful flowing shapes.
It's like there's some unseen force shaping things behind the scenes.
But really, it's just about following basic rules and interactions. Even something like a traffic jam clearing up is a form of self-organization. All those drivers reacting to each other, and eventually, the flow starts moving again.
Never thought about traffic that way. It's actually kind of comforting knowing that order can emerge from what seems like total chaos.
Right. And it's not just theoretical. We can actually use this concept of self-organization to design better systems. Think about cities that can manage traffic flow more efficiently using real-time data, or even supply chains that automatically reroute shipments if there's a disruption.
Now that sounds like something straight out of science fiction.
It does, doesn't it?
Yeah.
But it's closer to reality than you think. Now, Chapter 3 in Understanding Nature's Laws takes a bit of a turn. It talks about limits to growth, which might seem odd in a world that's always pushing for more.
Limits to growth. But isn't that like a fundamental law of nature? Everything has its limits.
It is. You can't have unlimited growth in a world with finite resources. It's like trying to fill a bathtub that's already overflowing. At some point, you got to turn off the tap.
So what exactly are these limits and how do they shape natural systems? I'm curious to see how this connects with what we've been talking about.
Well, the chapter starts by talking about growth itself. It makes a distinction between biological growth, like an organism getting bigger or more complex, and ecological expansion, which is when populations spread and increase within an ecosystem.
Okay, so biological growth is about individual organisms, while ecological expansion is about entire populations. But wouldn't both of those have some built-in limits?
Absolutely. The book points to two main factors: resource availability and environmental resistance. Like, imagine a garden, right? You plant too many seeds too close together, and they'll all be competing for sunlight, water, nutrients. Some will thrive, some will just wither away.
So even with the best intentions, there's only so much a system can support.
Exactly. And this applies to all living things, not just plants, even humans.
Like that story about Easter Island, right? A whole civilization collapsed because they used up all their resources.
A sobering reminder of what happens when we ignore those limits, and a perfect example of how everything's connected and how unchecked growth can have unintended consequences.
So it's not about stopping progress, but about understanding that growth can't just go on forever.
Exactly. It's about changing how we view progress, not just focusing on more, but on balance, sustainability, and what's good for both people and the planet.
And this is where systems thinking comes in, right?
Mm-hmm.
It helps us see those complex relationships and make better decisions.
Absolutely. When we understand those feedback loops, emergent properties, self-organization, and the limits to growth, we can move past those simple solutions and find ways to address those challenges in a more thoughtful way.
This is all incredibly insightful, but I have to ask about one more thing. It's something that really caught my eye in the reading list. The Gaia hypothesis.
Ah, yes. The Gaia hypothesis. Named after the Greek goddess of Earth, it proposes that everything on Earth, living and non-living, all interacts to form one giant self-regulating system.
Wow, that's a big idea. It's almost like viewing our planet as a single living organism. How does that fit in with systems theory?
Well, it takes a truly holistic perspective. It's all about the interconnectedness of everything, a powerful example of how systems thinking can be applied on a grand scale.
So what evidence is there to support this idea, and how do scientists view it?
Well, those who support the hypothesis point to things like how the salinity of our oceans has remained pretty constant, even though rivers have been pouring salt into them for billions of years, or how our atmosphere maintains a stable temperature, despite changes in solar radiation. It suggests there are mechanisms that regulate these things, keeping the planet habitable.
It's like Earth has its own internal thermostat, keeping things in balance.
In a way, yes. But it's important to note that the Gaia hypothesis is still being debated. Some see it as a powerful metaphor, while others believe it's a testable scientific theory.
So it's a thought-provoking idea that challenges how we understand our planet and its systems. Definitely something that needs more exploration.
Exactly. It raises some important questions about the interconnectedness of life on Earth and the need to look at things in a more holistic way. And this leads perfectly into the last chapter we're going to discuss today.
Great. What's on the docket? So we've covered these fascinating concepts of feedback loops and emergent properties, and even touched on the Gaia hypothesis. It's really changed how I think about our planet, as one big self-regulating system. But I'm wondering how all this applies to us, to human systems.
That's where it gets really interesting. In Chapter 5, The Flow of Energy and Matter, Cycles and Networks, Understanding Nature's Laws, takes a look at how energy and resources move through systems. Super important stuff when we're talking about sustainability.
I can see why that would be relevant. I mean, we need energy and resources for, well, pretty much everything. But we rarely stop to think about where they come from or where they go when we're done with them.
Exactly. The chapter reminds us that when it comes to matter, Earth's basically a closed system. What we've got is what we've got. No new deliveries from outer space or anything.
So it's like we're playing a game with a limited set of building blocks. We can rearrange them, but we can't just magic up new ones.
Spot on. And the same goes for energy, to a certain extent. Sure, we're constantly getting solar energy, but we still have to be smart about how we use it and what happens to the byproducts.
Yeah, and we're seeing the consequences of that with climate change.
Yeah.
But how can understanding these cycles and networks actually help us create a more sustainable future?
Well, the book highlights this key principle from nature. Waste equals food. In natural ecosystems, one organism's trash is another's treasure. Nothing goes to waste.
That's so different from how we do things. We create tons of garbage and pollute our environment with all the stuff we consume.
Right, but that's where nature can be our teacher. Take the idea of industrial ecology, for example. It's all about designing industrial systems that mimic the circular processes we see in nature. Less waste, more efficient use of resources.
So instead of that straight line of extraction, production, consumption, disposal, we'd be aiming for a more circular model, where what we think of as waste becomes a resource again.
Exactly. And this way of thinking can go beyond just industries. How we design our cities, manage our food systems, even our own personal consumption habits.
It's like a complete shift in mindset, isn't it? Going from a sense of scarcity to a sense of abundance by recognizing how everything is connected.
It really is. And that leads us to one of the most powerful things about systems thinking. It helps us solve complex problems in a smarter, more effective way.
So how can we actually use systems thinking to tackle real-world issues?
The book gives some great examples. Let's take traffic congestion, something we mentioned earlier. A traditional approach might be, okay, let's build more roads, wider roads. But a systems thinker would ask, what's really causing this congestion? How do things like commuting patterns, public transportation, even urban planning decisions all contribute to the problem?
It's about looking at the whole picture, not just treating the symptoms.
Precisely. When you map out the system, identify the feedback loops, consider unintended consequences, you can come up with solutions that address the root causes, not just the surface stuff.
So it's not about quick fixes, it's about long-term solutions that are more sustainable and resilient in the long run.
You got it. And we can apply this systems thinking approach to so many different challenges: climate change, poverty, healthcare, education.
This has been an amazing deep dive. I feel like I have a whole new way of understanding the world now.
And remember, this is just the tip of the iceberg. There's a whole universe to explore within systems theory and complexity science. But hopefully this has sparked your curiosity, giving you a solid starting point.
So to our listener, as you go about your day, think about the systems at play in your own life. Where do you see feedback loops? Can you apply the principles of self-organization or cyclical resource use? Start thinking in systems, and you'll see the world in a whole new light. Until next time, keep exploring.